Good morning, everyone. We are going to continue the last session in chapter 7, which is related to the head losses in enclosed pipes or in enclosed conducts, and with the minor head losses that we have in the pipes. As we mentioned before, we said that we have in the, just a minute. Okay. The previous lecture, we talked about the head loss and the type of head losses that we have. So in general, we have two types in head losses. The main head loss that we have is due to the friction, and it's called friction head loss. Yes, so the head loss that we have, head losses. In general, there is two types of head losses, main head loss and minor head losses. The main head losses that we have is due to the friction, or let me say in another way, it's due to the length of the pipe. Yeah, so this is due to friction, head loss, or it means that due to the length and diameter of the pipe, roughness of the pipes, and we said that could be a Darcy-Weisbach equation will control by this, and we will say that the head loss, the friction head loss, is equal to rho friction factor, the length divided by the d, the v square divided by the 2g, and this f could be found by we have either type of flow. If it was laminar, and then it will be laminar, and it will turbulent. There will be the laminar. We will have 64 divided by Reynolds number. We know that the Reynolds number is equal to V R over nu. And if it was non-laminar, so there was either we have smooth or rough pipes, and this could be controlled by Colebrook or Moody diagram. This is all what we have in the minor head losses, main head losses. The other part of the head losses that we have is called minor. The minor head losses is usually we are as a designers, and we are when we have a network more than 1,000 meters in length, so we will not consider that much. It will be less than 20% of what we have on the friction head loss. So what we have to do is we will find the friction head loss that we have, and we will add more 20% of that one, or we will multiply it by 1.2. Then we can consider that is a total head loss. So the head loss is called the friction head loss plus the minor head loss. This is H minor. Now in this chapter, today we are talking about the minor head losses. What are the minor head losses? The minor head losses are usually coming from the fittings that we have in the pipes of the pipe connections that we have, pipe connection that we have in the networks, connections. What are these kinds of the connection and the fitting that we have? I think you are all remember this this experiment. We did that experiment in here's the experiment that we did. Here in this experiment we did lab number 5. We have a flow. This flow is coming from this pipe. It will go through the pipes. So what we did, we found the head loss between these 2 points with different, the length is 1 meter, but the diameter is known. But for these 2 pipes, we have a rough pipe. For these 2 pipes, we have a smooth pipe and so on. So the other thing that we can use this experiment for is to find the fittings. Here's, for example, one of the fittings that we have. This is called ball valve. Is a valve used to control the flow, to close the flow, and it's inside this one. Inside this valve, there is a ball-like, a hollow ball-like. So it is look like this. And there is a hole inside this this valve. This is a hole, and when it's closed this way, so the hole this will help to close the hole, and the wall pipes will be stick together. Then there will be closing, and if you want to open that one, you just turn that bulb valve. So the main point that we have, it's a ball, and like a marble, but hollow thing. And then you can use it to control the flow. Now, also we have fittings. For example, we have this kind of fitting. It's called elbow. Elbow, it's coming from this one. We have this elbow, our hand, and this is also make a kind of head losses. We have also T, this is called T connection. And also we have, here's we have, if you have, just look at closer. Again. Yeah, and the number 11, we have the diameter of pipe here is 25. The diameter here is 40 millimeters. So what will be happen? There will be a sudden enlargement. This is called sudden enlargement. The sudden enlargement is that, sorry. The sudden enlargement is the diameter is coming from close, small to greater. Here in number 15, we have sudden, let me say, narrowing, sudden narrowing. So we have in 14, it's going to 25. This is also a kind of fittings that will affect on the pipe. Now, what are this kind, or how can we measure the head loss through these pipes? It will be a kind of, let me say, the velocity will act a very important role in how to calculate the minor head loss. So in general, the minor head losses could be a function of the velocity. So the minor head losses in general, this is a minor head loss. It will be a function of velocity. Which velocity? Kinetic velocity. Here's the velocity, but there is a coefficient here. Coefficient. This coefficient is called minor coefficient for that device that we are using. My minor. The minor, let me say, the head loss that we have, for example, if I want to consider this, I will say the minor head loss through a certain valve, it is equal to the velocity in this valve square over 2g times its coefficient. Which kind of coefficient? It depends of the K, it's called K coefficient, but this K coefficient depends on the type of the valve that we have. Uh, let's go back to the lectures. You can see here's one of the type of the head loss. Yeah. So this is the minor head losses that we have. I say that we have in, when we have the length of the pipe is greater than 1,000 the diameter of, here's, for example, the network that we have. If this L, the length of the pipe, and we have the D is the diameter of this pipe. When the length is greater than this D by 1,000 times, we can also neglect the effect of this minor losses. This is very important thing. Then you can say, for example, you have a reasonable thing that you can say, I can neglect the minor losses because the length of the pipe is very high, or it's greater than 1,000 of the diameter. But in general, the minor losses will be a function of this energy, which is a kinematic energy. And this case belong to the coefficient of the minor connection. Now, let's check the details of the minor losses. The minor losses, we say that it will be due to the fittings. The fittings are the apparatus or some kind of device or link used to connect the pipes. For example, we have sudden contraction or gradual contraction. So this will be due to the contraction. Contraction, it means that we have a greater diameter, and this greater diameter with the pipe is going to be contract. So we have D1, we have D2. So what will be happen? The flow is going from this way to that way. So the diameter is suddenly or gradually will be contracted. We have entrance. It means that we have entrance. For example, if you have a tank and you are connecting a pipe to this one, we have an entrance losses. So this will be an entrance. This is a kind of connection. Enlargement, it's exactly opposite to the contraction. Exactly. Enlargement, we have a smaller diameter, and suddenly or gradually it will be enlarged. And then there will be sudden, there will be gradual, there will be an exit. An exit, it means that you will have a pipe, and this pipe will go through the flow inside this pipe to another reservoir or another tank. That tank that will have a large diameter, which could consider that the velocity in this tank can be 0. Also, here's all but the elbows bend. So the bends, T-bends, for example, elbows are called fittings. Now I will give you some details, and we will let others away. For example, the first head loss that we have due to the contraction, the definition of this contraction is that we have a higher diameter in value, and there will be a smaller in value. And then you can see here's the wall. There will be a wall. This is the pipe that we have, the yellow thing. This is the pipe wall. So what is going on? The flow is going from here, and there will be, this is a kind of short circuiting. It means that the flow is going to turn around itself here. So it will make a kind of eddies. Short circuiting, it means that the water is coming and going this way in this space. Also, after that, this is the stream. There will be also a small kind of shortcutting here. So this will help, let me say, will make a kind of head losses. Now, this is the hydraulic gradient line. This is the energy gradient line. We say the energy gradient line is Z plus P over gamma plus V1 square over 2g, right? So this is at this point. Then after there will be a contraction, there will be a V2 square, because the V1 is very small, the V2 is very high. Because why? Because the same Q that we have. So when we have a small greater diameter, it means we have a smaller V. So V1 usually is less than V2. So that means this will be higher than this one. But we have the gradient line will be less. Anyway, this is the coefficient. In this way, we can find the head loss due to that sudden contraction. So the sudden contraction is a function of velocity downstream. Be careful that the head loss here, due to this one, due to this contraction, is a function of VU2 square. So means higher V2, it means higher minor loss. Greater, it means that when we have V, it's great. So it means that the minor head loss due to that contraction will be higher than, and there is a coefficient, it's called Kc. K is for constant, C is for contraction. And this contraction, this Kc is sudden contraction coefficient, and it depends on the velocity and the d2 by d1. This is the d2, and this is the d1. Okay. There is another kind of contraction. Instead of having this way, instead of having this sudden contraction suddenly, we have a gradually. The gradually, it will be like this. We have V1, we have V2, so there will be a gradual, the gradually contraction. And also this head loss, it depends on the D2 divided by D1 over D2. And also it will be a function of the velocity in the downstream in this one. But I mean, we call this K coefficient of contraction prime because it's for a gradual contraction. If it was suddenly, it will be Kc, but and also both of them are depending on V square. Okay. Now you can see there is this contraction, this Kc prime also depends on the value, this angle, and it will act. And I think we have a table for that. This is first type of minor losses. So for minor losses, we have a contraction. Contraction means we have higher diameter and we have smaller diameter. So either we have gradual or either we have like this. Now, the second thing that we have part is the entrance. Entrance, it means that if you have this reservoir or this tank, so we are connecting a pipe through this one, so there is an entrance, entrance, it means that the pipe will start entering the network. The flow is going to enter the network through this entrance. So entrance is also a kind of making minor head losses. This minor head losses, as we talk about, it's equal to coefficient of entrance times the V square over 2g. Which kind of V? The velocity, here's the velocity. The V that we have here. And we have, if the pipe is just linked to the wall of this reservoir, this K is equal to 0.5. If it was, let me say, it's extended inside the pipe, the KE, it will be 1. Why we have more greater the coefficient of, so greater KE, it means more head losses. So why we have in this KE is greater in 1 and here is greater of 0.5, because the water is tries to go through this tank by the pressure to this pipe, but it will find there is barrier. So it could be like this. It needs to turn around and then go, and this means that it will lose more energy. That's why we have KE is greater than this one in this case. The best thing that we have, the connection, it will be like this. Rendering or hatching hatching these angles. So it will make the head loss will be very less than we expected. And it's due to the R, the curvature that we have here. So 0.05, it means that the head loss here is less than 20 times less than this way, because 0.5 divided by 0.04, it means that 50 divided by 4, it's about 20 to 12.5. We have 12 times the head loss here is less than the head loss here by 12.5 times because of these small hatchings. So if we want to, let me say, minimize the head losses, we have to take care about these coefficients. And also there is a kind of special entrance. We have this kind of connection. Now, this was the second thing. The third thing that we have, the third point that we have, the opposite of contraction is enlargement. What that means we have a pipe with a specific diameter, and there will be suddenly it is enlarged to another diameter. So D2 is greater than D1. This is called enlargement. The enlargement here. Then also there will be, due to this enlargement, there will be a minor head loss. But the main point between this minor, the contraction, enlargement and contraction is that in contraction, the minor head losses, it will be a function of V squared, 2 over 2G K contraction. This is because the downstream velocity. While we have for enlargement, the minor head losses will be a function of V1 minus V2. You know, here's velocity is greater than this velocity because the diameter here is very small and here's diameter is very high. So the V1 is greater than V2. So the difference in velocity will act on this head loss. More differences in velocities means more head losses. And there is no coefficient for enlargement. Be careful, there is no any coefficient for minor loss. So we say that here we don't have any K. There's no any K. There's no any K, for example, enlargement. There's no anything like this. But we have to focus on the velocity on both two downstream and upstream and squaring them. Also, this is called sudden. This is sudden enlargement. Suddenly, the diameter suddenly will be changed from smaller value to higher value. While we have gradual enlargement, means this is gradually will enlarge. Also, it will depend on the V1 and V2 ratio. But here we have a coefficient at enlargement. And this coefficient of enlargement, it will depend on the angle that we have. Here's the angle. We should take care about this angle. So how much is this angle? Is it a 10, 20, 30? So for each of them, there will be a coefficient of more coefficient. So now if it was 90, it means that this is going to be a sudden enlargement, okay? Now, we say that we have, till now, we have sudden entrance, we have sudden entrance, we have sudden contraction, gradual contraction. We say that we have entrance, This is, we have three types of entrance, and we have enlargement. And also we will take another kind of minor losses, which is called exit, which is the opposite of entrance. So we have entrance, and there will be a tank, and this tank, there will be a pipe that taking water from this reservoir or this tank. The entrance is that you have a pipe. This pipe will throw in its flow through another pipe, another tank. This is called the entrance. And this entrance, the coefficient, it's called KD, which belongs to discharge coefficient. Oh, look at this one. The velocity here is a function of this head loss. So the more velocity, because the velocity could be equal to 0, then by the way, we can say it's a kind of enlargement. In enlargement, we say that V1 minus V2 square over 2G. So in this here, we have V2 is equal to 0. So it's a V1, which is V square over 2G times the coefficient of discharge. The coefficient of discharge means the shape. This shape, it will depend. If in case that we have, look at this example, where the exit discharge loss coefficient is equal to 1. Why is equal? If the velocity here is 0, means there is a stagnant water, then we can consider the KD in general equal to 1. Now, this was the fourth type. Also, for the fittings, all the fittings that we have, for example, globe valve, angle valve, close and T, a connection, all of them, we have the V square over 2G. This belongs to the velocity in the connection, and there will be a coefficient of the fitting. For example, for globe valve, we have the K is 10, based on what? The L over D, the length of the pipe divided by D. If it was 350, then the K is 10. Now, what that means? That means if I have this globe valve, this is a globe valve. So if I want to check the head loss after the valve and before the valve, there will be a head loss change in the head loss. The head loss in the minor head loss is equal to K times V square over 2G. We know the velocity in this valve. So the K that we have is the fitting, the fitting coefficient of this valve, and it will depend on the length of the pipe that we have it in and the diameter. And it will be equal to 10 if this 3L over T was 350. Now we have another thing. We have for angle valve, we have for T. For example, for T, we have 1.8 if the L over T was 6. So these are the all fittings that it will for each of these kind of fittings. The bends in general, bends we have, so sometimes you have pipes going this way, and we have to bend this pipe like this, and we go this way. So what will be happen due to this bend? This is called bend. This bend, we have to consider there will be the coefficient is KB, which is for bend coefficient, is the velocity square over 2G times the coefficient of this bend. And this coefficient of the bend, it depends on the diameter of the pipe, and it will depend also the curvature, the R, the curvature that we have. So this R over this D, if it was here this way, now, for example, for smooth pipe, bend of 90 degree, the value of KB will be various in this way. This is only for small pipes. So when we have smooth pipe, there will be R over D. So based on that R of D, there will be a K of B or bent K. Now, if it was not a smooth pipe, rough pipe, we have to use this R over D. And this is the smooth one, and this is the other KB. So this is for K bend. Okay, now look at this example. In this example, we want to find the head loss from this point to that point. So first of all, we have to consider that we have two types of head losses. The head loss due to the friction plus the head loss due to the minor one. The friction is that we have the pipe from here to there, and you can see we have two pipes. So we can from here to there and from here to there. So we have to consider this part and this part along. So we will have to find the head loss friction from this pipe and the head loss friction from this pipe. And for each of them, we have to use it's L over D V square over 2G times the friction coefficient of this pipe. Also, we have to use, so what we have to do, we have to have their lengths from here to there, and their diameter and their length and their diameter. And because it's a smooth pipe, we have to consider this one in our calculation. So the smooth pipe consists of 12 meter of a 118 diameter pipe followed by, so look at this one, 12 meter of 100. So this part is 12 meter length and its diameter is 180 millimeter, while this part is 75 meter and it's 550. So we can say length, this is diameter, or phi. So what happened here, we have there is a sudden what? Hello? What we have here in this connection, we have a kind of sudden enlargement, right?
Enlargement.
Yeah. Now, this could be considered. We have an entrance, the water is going to enter this pipe from here. So we have also a minor head loss due to the entrance. We have a minor head loss due to sudden enlargement. And also there's a minor head losses here due to the exit. Now, other thing that we have minor head losses, we have those three ones. Also, we have the friction from this pipe and we have the friction from this pipe. Now, the entrance is a flash and discharge submerged if it's once, and the velocity here is very important thing, that the velocity in the type 1 is 5.7 meter per second. So we have the velocity here, 5.7. So we have the velocity, we have the diameter here. It means that we have the area here, and then this velocity times this diameter. It means that we have the Q in this pipe, which is the same Q that's going to the second pipe. So, and I have the diameter in the second pipe, so it means I can find the velocity here, because it's very important to find the velocity in this pipe and this pipe for the minor head loss, and also for the friction head loss. So the first step is to find the head loss, is to know the Q, the discharge. The discharge, as we know, the discharge here is equal to, in this pipe, the discharge is equal to velocity times A. Where is the velocity? It's given to you, it's 5.7. And where is the A? The A, we know that the phi here is 180 millimeters, so pi d square over 4. The pi is 18.18. So this is 0.18 pi d square over 4 times the V is Q. So this Q, which is 0.14, will be the same Q that's going to the pipe number 2. So for pipe, because of the continuity equation, now I have the area and I have this Q, so I will find the velocity in the second pipe. Now I get the second pipe velocity. So what I know that we should take care about this on. So the velocity here is 0.14 1 meter per second. Sorry, this is the Q. The velocity here, V1, is equal to 5.7 meter per second. And the velocity here is 0.611 meter. And you can see the velocity here is less than this one because of what? Why we have the velocity in the second pipe is less than velocity in the first pipe?
Because of changing diameter.
Yeah, we have larger diameter means less velocity. True? Is it true? Larger diameter means less flow.
Yes.
Now, I have this velocity, I have this one. So I have to, so now consider, we have to find the friction head loss first. A friction head loss will be considered F L over D V square over 2G. I have for each of them, it's their velocity. So their length are given to me. The length here is 12 meter and the length here is 75 meters. So I have to consider that one. So I have to find, so I have the L, D, V, and V. So what should I know that not to find the F? We have to find the F first and then consider the F, HF. To find the F, I have to check whether we have a laminar or we have a turbulent flow. So to check that laminar or turbulent flow, what should I do? I have to find, hello? What should I do? Type of flow. It means how to find the F. We have to find the Reynolds number. Reynolds number is equal to rho V R nu or rho V rho D over nu. So D1 V1 over rho. Now D1 is the diameter of the first one and V1 is 5.7 divided by the viscosity of water, because at 50 degrees, this is the viscosity. Now you can get this Reynolds number, which is greater than what? Greater than 4,000 means the flow here is turbulent. Now the R2, it will be definitely V2 D2 over nu, which is also will be 2.5, which is also greater than 4,000. Also, we have turbulence. So the flow in both types are turbulent. For turbulent flow means the F we have to find the F. So from the Moody diagram, I can use this one. This R 9.1 times 10 to the power 5. This is the R. And we have E over D 0. So from 9 times 10 to the power 5, I will go to the Moody diagram and I will find the Reynolds number there. Sorry. 9 times 10 to the power 5. Here's the 9 Moody diagram. So 9 times 10 to the power 5 means 90,000. This is the 9. 10 to, and because it's a smooth, this is for smooth pipe. So what will be happen? This is will be the F. So it will be 0.015, 016, 017, 018, 019. So it will be 0.018 something. This is the friction for the first pipe. For the second pipe, we have the R is 2. It's about 2. So we have this is the F. And this is will be the second part, the green, yeah. it will be the friction coefficient for the second part is how much? 0.025 to 0.025 0.0252. So 0.018 and 0.0252. Back to the lecture, 0.025. Yeah, 0.025. It's about, yeah, we have these two ones. 1.8 or 0.2545, yeah. Anyway, we have these two fifths, and because it's a smooth pipe, we can consider that one and use the head loss. Now, this is for the head loss here, minor head loss is equal to 0.018. L over D, the L is 12 millimeter, D is 0.18, V1 square, which is 5.7 square over 2G. This is the friction head loss for the first pipe. The friction coefficient for the friction head loss for the second pipe is equal to its F, which is the 0.0145 times L, which is 75, divided by the diameter. I think it's 554.55. V1 square, we have the V in this pipe is 0.145 square over 2G. Now, what else? This is only the friction head loss. We have these two ones. Now, what else I have to find? I have to find the entrance. The entrance, it will be considered R1 V square over 2G. So what should I do? Here's we have the 1 is the coefficient of entrance. And because it's multiplied by, yeah. Now, this is V square over 2G. So K is times this one. And also there will be, sorry. Yeah, this is one, the second one. Look at this one, the entrance that we have here. The entrance that we have here, that we have sudden enlargement. The sudden enlargement, we say that it depends on the V1 and V2. So V1 here is squared minus V2 squared divided by 2G. And the second thing that we have in pipe 2 here is the friction coefficient here. And there is also exist, or let me discharge coefficient, which is 1 V2 square over 2G. Overall, there will be 3.5 meter, the total head loss from this part to that part. Okay. So what I did, in the before, if you want to neglect the minor head losses in this question, what will be gonna do? If I'm going to neglect the minor head losses, will go to be 0. Will be going to be 0, and this one is going to be 0. This is what if I have neglecting the minor head losses. But if you don't need, or if you don't have to neglect this one, you have to calculate them. And why we have the K entrance is 0.5, because the type of entrance here. This one, this shape here is exactly what we have here. Yeah, this is exactly the shape that we have here. So that's why we have V square over 2G times 0.5. Yeah. So 0.1 times V1 square over 2G, and this is also FL over 2. So the way that it can be written, this is V1 square over 2G times KE plus the V1 square times 2G. This is the friction, this is the minor. And also we have here the enlargement. And this is also the V1 square of V2 square over 2G times FL over T. This is the friction head loss. And this is the KD. KD is the discharge coefficient because the velocity here could be also 0, and this is also could be, this is the, in this case, that KD will be equal to 1 when we have the exit discharge loss coefficient. Any question regarding this example?
No, sir, thank you.
Is it clear to you?
Yes.
Good. I want you just to check the second question. In this second question, we have the, now in this question, I have the head loss. A 320 millimeter diameter, this is the 320 millimeter, the phi. And we have the L is 140 millimeters and the friction coefficient is equal to 0.025. Runs from reservoir to another. So we have entrance, we have exit discharge, and under the water. The intake is square-ended. The intake is square-ended, and the difference between the water surface level at the two reservoirs is 36. This means the head loss, the total head loss, which is the minor plus the friction head loss. So this is called the head loss. The total head loss is 36 meters. So find the flow rate. This is very common questions that usually it will ask you due to the difference between the reservoirs. We want to know how much is the Q. So we have 36 meters. This 36 meter is going to be considered, it's a kind of length of, this is the V square over 2 G L over D. This is the minor, the friction head loss. Plus we have two minor head losses, the existent, the entrance, which is its K equal to 0.5, this K times V square over 2G, and the discharge coefficient, also KD times V square over 2G, which is 1. So due to the head loss that we have 36 plus these minor head losses, we can get this one. So you can just find the V. So from the V, we have the V, then the V, I have the diameter, which is 320. I can find the Q directly. Okay, this is for part one. For pipe, and the pressure in the pipe is at 0.95 meter from the intake, where the elevation is 39 meter. So at this point, I want to see how much is the, at this point, there will be the pressure. Is the head. So to find the head here, it means that you have to find the head here, which is 36, minus the head loss from here to there. So we have the length. The length is from to point P, it's 95 meter. It's not 140, it's 95. So what we should do, we have to find 0.5 is the entrance, 95 is the L, this is the D. V square over 2G, we have the velocity. Then we can find the head loss due to the friction head loss and the minor head loss, and it's in 39, it will be the total head loss. P over gamma, V square event is equal to 2.9. So we can just find this is the pressure at point B, P. Okay. Thank you for attending, and if you have any question, I'm ready to answer you all.
Sir,